Chapter 2: The Physical Layer and Data Link Layer. 1. Physical Layer Network Equipment Types. A. Data Terminal Equipment, DTE, refers to user equipment that convert outgoing user data into a transmission signal, and convert back the incoming signal into user data. Example: terminals, terminal adapters, personal computers, and mainframes. DTEs commonly reside at user sites. Conted. B. Data Circuit Terminating Equipment, DCE, refers to the network equipment that connect DTEs to the network communication lines. A DCE may be a part of a DTE or be an entirely separate device. Modems and multiplexers are all examples of DCEs. Signal type and transmission. Transmission is the act of transporting information from one location to another in the form of signal. The signal may be analog or digital, and may travel in different media. Multiplexing and demultiplexing. The technique of allowing multiple signals to be transmitted at the same time over the same cable is called multiplexing. The role of a multiplexer is to accept data from more than one source and transmit it over the shared channel. The demultiplexer accepts data from the shared channel and sends it into its more correct destination. Cont. The two main types of multiplexing: time division multiplexing, TDM, and frequency division multiplexing, FDM, both aim to maximize the number of message signals that can be transmitted over the shared transmission link. FDM was the earliest and least sophisticated method of multiplexing and can be employed only if the data is being transmitted in analog form. Because the analog data communication does not necessarily use the entire bandwidth of the communication channel, it offers the possibility of dividing the bandwidth of the line into independent, permanently assigned lower speed subchannels that operate on particular frequencies within the spectrum. FDM. TDM divides time into slices called time slots, to separated channels. With TDM, each computer takes its turn at transmitting and receiving data. The order in which the multiplexer serves the computers is fixed. Depending upon the multiplexer type, the device accepts only one bit, byte, or packet of data from each input line, puts it into a specifically allocated time slot on the high-speed transmission line, and then moves on to the next terminal in the sequence. TDM. Physical layer standards. Two very popular standards for connecting DTEs and DCEs. A. The analog standard RS-232 for serial line communication. B. The digital standard X.21. A. RJ45 connectors for Ethernet. IS data link layer on OFTO-S model. Transforms the logical communication channel provided by the physical layer into a reliable channel by splitting the data into frames which are subjected to error control and flow control procedures. Data link protocols are divided into synchronous and asynchronous. Synchronous protocols operate by delimiting user data with unique bit patterns which the receiver uses to detect where the user data begins and where it ends. Synchronous, clock-based, protocol is either character-oriented, user data is a sequence of delimited characters, or bit-oriented, user data is encapsulated biframes. In a bit-oriented protocol, a specific character set is assumed. The unit of transmission is a frame which consists of user data, an arbitrary bit sequence, control data, address data, error checksum and delimiting bit patterns at the other end of the frame. Asynchronous protocols are a character-oriented and operate a behaving the transmitters around each character with a start and a stop bit. These bits indicate to the receiver where the character starts and where it ends. The receiver extracts the user data by removing the start and stop bits. Conted. Link layer protocols comprise a number of functions: acknowledgement, to ensure that data is correctly passed on by stations, timers, to impose time limits on operations, error checking, to facilitate error-free transmission, retransmission, to overcome errors, and flow control, to manage the differences in device speeds. Cont. Error checking. No transmission medium is perfect. Whether the data is transmitted using UTP/STP cable, coaxial cable, fiber optic cable, or wireless networking, the transmitted data will be subject to noise. A number of schemes exist for detecting errors in data communication. Cont. Types of error 1. Single bit 2. Multiple bit 3. Burst. Detection error detection uses the concept of redundancy, which means adding extra bits for detecting error at the destination. To detect or correct errors, we need to send extra, redundant, bits with data. Cont. Detection methods: I vertical redundancy check, VRC, 2. Longitudinal redundancy check, LRC, 3. Cyclic redundancy check, CRC, 4. Checksum. Cont. Parity checking: at the end of each character an extra bit is appended, known as the parity bit. The value of this bit is chosen so that the total number of ones in the character is even parity, or odd parity. For example, if the sender is transmitting the character 111010 and using odd parity, the parity bit will be set to 1. The receiver examines the received character, and if the total number of ones is odd, assumes that no error has occurred. CRC, the most powerful of the redundancy checking techniques, is based on binary division. Given a k-bit data sequence, then sending computer generates an extern bit sequence, known as the frame check sequence, FCS. The extran bits are generated so that their salting sequence, consisting of and n bits, is exactly divisible by some predetermined number. Cont. The receiving computer will divide the received sequence by the predetermined number, and if there is no remainder, assumes that there was no transmission error. The CRC error checking scheme can detect, but not correct for, almost all transmission errors. Checksum is used by the higher layer protocols, TCP/IP, for error detection. To calculate a checksum, I divide the data into sections. 2. Add the sections together using 1's complement arithmetic. 3. Take the complement of the final sum, this is the checksum. Cont. This technique works by considering the data stream as a sequence of integer values. After the sending computer has transmitted an integer values, the arithmetic sum of then integers is computed and transmitted. The receiving computer computes the same sum and compares it against the received checksum value. Checksum can normally detect, but not correct for, multiple bit errors. Flow control refers to the regulating of the rate of data flow from one device to another so that the receiver has enough time to consume the data in its receive buffer, before it overflows. 2. Type I stop and wait, send one frame at a time and wait for AKN2. Sliding window, send several frame at a time. Error control the data link layer is based on automatic request which is 3 transmission of data. Type go backend requesting the retransmission of the faulty frame as well as all succeeding frames. Selective reject upon encountering a faulty frame, the receiver requests the retransmission of that specific frame. Cont. They handles damaged frame lost data frame lost acknowledgement. Error correction Hamming code. The Hamming code is a single bit error correction method using redundant bits. The number of bits is a function of the length of the data bits. In the Hamming code, for a data unit of m bits, use the formula 2r greater than or equal to m and r plus 1 to determine r, the number of redundant bits needed. Data link layer standards. The two popular standards, A, the BSC, or BiSync, protocol is a character-oriented protocol devised by IBM for half-duplex communication. B, the high-level data link control, HDLC, is a bit-oriented protocol with a number of variations, LAP, LAP-B, LAP-D, and LLC. It supports half as well as full duplex. It transmits information in frames, of which there are 3 types: information frames, supervisory frames, and unnumbered frames. Blank. Switching method. Switching is a method in which multiple communication devices are connected to one another efficiently. A switching in intermediary hardware or software that links devices together temporarily. There are techniques: toast tablish communication, link SINA communication network. Cont. There are 3 fundamental switching methods: circuit switching, packet switching, and message switching. Packet switching. In this mechanism, a message is split up into packets of a fixed size. Besides the blocks of data to be sent, a packet has a header that contains destination and source addresses, control information, message number, number of current and last packet, acknowledgement, and error checking. Bytes. Packet switching is generally more efficient than circuit switching for novice communication. Cont. There are two popular approaches to packet switching. Datagram approach, virtual circuit approach. Switching. Virtual circuit, SVC. Permanent virtual circuit, PVC. Datagram approach. In the datagram approach, each packet, called a datagram, is treated independently from all other packets. A packet is routed independently of other packets. Packets belonging to same message may take different routes. Packets can arrive out of sequence. Routing decisions made at each intermediate node. NB. In a packet switched network, there is no resource reservation, resources are allocated on demand. Virtual circuit, connection-oriented, approach. In the virtual circuit approach, all packets of a message or SIN follow the exact same route. Virtual circuit packet switching is implemented in two forms, SVC and PVC. A route is set before any packets are sent. Each packet header has a virtual circuit identifier. No routing decision made at intermediate node. Sequencing of packets. Circuit switching. Circuit switching involves three phases: circuit establishment, data transfer, and circuit termination. Only you are using the circuit at that given time. Telephone call. A circuit switched network is made of a set of switches connected by physical links, in which each link is divided into channels. In circuit switching, the resources need to be reserved during the setup phase. The resources remain dedicated for the entire duration of data transfer until the teardown phase. Message switching. Message switching, often known as store and forward switching, accepts data messages, stores the messages, and then forwards each message to the next destination or node when the circuits become available. This means that each message is using at most one link at any given time, but may require more storage buffers in intermediate nodes. Message switching techniques were originally used in data communications. Email delivery is another example of message switching. In voice systems, you can find voicemail delivery systems on the internet. Cell switching and concept of ATM. Cell switching is similar to packet switching, except that the switching does not necessarily occur on packet boundaries. This is ideal for an integrated environment and is found within cell-based networks, such as ATM. Cell switching can handle both digital voice and data signals. ATM is a connection-oriented packet switching technology that achieves fast packet switching with small packets of fixed size. In ATM, the packet is called a cell because all packets in a given network are of fixed length. ATM is designed to provide semantic transparency, correct delivery of information, time transparency, the timely delivery of information. Cell switching in ATM networks is carried out at the ATM level. Comparisons: CS and PS. Circuit switched, packet switched, line resource performance, cost, adaptive routing, switch device reliability, utilization, dedicated, shared, guaranteed, averaged, expensive, less, not easy, easy, highly complex, simple, high, higher, low, higher. Framing. The data link layer needs to pack bits into frames, so that each frame is distinguishable from another. Our postal system practices a type of framing. It contains flag, header, data from upper layer, trailer, flag. Byte stuffing is the process of adding one extra byte whenever there is a flag or escape character in the text.i.flag. ESC. Ethernet. Ethernet has become the most popular way of networking desktop computers and is still very commonly used today in both small and large network environments. Standard specifications for Ethernet networks are produced by the Institute of Electronic and Electrical Engineers, IEEE, in the USA, and there have been a large number over the years. The Ethernet media was passive, which means it required no power source of its own and thus would not fail unless the media is physically cut or improperly terminated. More recent Ethernet standards have different specifications. Packets in Ethernet networks are referred to as frames. Cont. Frame formatting preamble SFD destination address source address length data FCS 7 bytes 1 byte 6 bytes 6 bytes 2 bytes 46 to 1500 bytes 4 bytes. Cont. Each frame begins with a 7-byte preamble. Each byte has the identical pattern 10101010, which is used to help the receiving computer synchronize with the sender. This is followed by a 1-byte start frame delimiter, SFD, which has the pattern 10101011. Next are the source and destination addresses, which take up 6 bytes each. The data can be of variable length, 46 to 1500 bytes, so before the data itself there is a 2-byte field that indicates the length of the following data field. Finally, there is a 4-byte frame check sequence, used for cyclic redundancy checking. Therefore, the minimum and maximum lengths of an Ethernet frame are 72 bytes and 1526 bytes respectively. Cont. The general features of Ethernet LANs. Pito redescription traditional topology line arbus other topology starbus type of communication baseband AX method CSMA/CD tran FERS PEDS 10/100/1000 Mbps cable type thicknet/thinet coaxial or UTP SSE. Cont. The first phase of Ethernet standards had a transmission speed of 10 Mbps. Three of the most common of these are known as 10^2, 10^5, and 10^T. The following table summarizes some of the features of each specification. Cont. Ethernet standards 10^2, 10^5, 10^T topology bus star bus C able type thinet coaxial thicknet coaxial UTP, Cat3 or higher, simplex/half/full duplex half duplex half duplex half duplex data encoding Manchester, asynchronous Manchester, asynchronous Manchester, asynchronous connector BNC DIX or AUIRJ45 Ma X segment length 185 meters 500 meters 100 meters. Cont. The next phase of Ethernet standards was known as Fast Ethernet, and increased transmission speed up to 100 Mbps. Fast Ethernet is probably the most common standard in use today. The Manchester encoding technique used in the original Ethernet standards is not well suited to high-frequency transmission, so new encoding techniques were developed for fast Ethernet networks. Cont. Fast Ethernet standards 100 base T for 100 base TX 100 base FX topology starbus CA BLE type UTP, Cat3 or higher, UTP, Cat5 or higher, fiber optic connector RJ45 SC, ST, or FDDI mic max L. Segment length 100 meters 2000 M communication type half duplex full duplex M. Cont. The most recent phase of Ethernet standards has increased transmission speeds up to 1000 Mbps, although sometimes at the expense of some other features, such as maximum segment length. Because of the transmission speed, it has become known as Gigabit Ethernet, and the most common standards are summarized below. BE Cont. Gigabit Ethernet standards 1000 base T 1000 base CX 1000 base SX 1000 base LX topology starbus CALE type UTP, Cat5 or higher, Twinax, shielded copper wire, fiber optic connector RJ45 HSSC max. L segment NGTH 100 M25 M275 M316-550 M communication type full duplex. CONT. Finally, the IEEE has also published a number of standards for wireless Ethernet networks. The original standard was known as 802.11, was very slow, around 2 Mbps, and was quickly superseded by more efficient standards. 802.11 now usually refers to the family of standards that followed after this original standard. Cont. Wireless Ethernet standards 802.11b 802.11 802.11g MX. Speed 11 Mbps 54 Mbps 54 Mbps AVE. Speed 4.5 Mbps 20 Mbps 20 Mbps Ma OX distance outdoors 120 M30 M30 M Ma IX distance indoors 60 M12 M20 MBFR roadcast frequency 2.4 GHz 5 GHz 2.4 GHz